Hello, folks. A wonderful evening to all the joinees. I hope you all are doing good and staying safe and healthy. Today, we have most respected Ambrish sir, Microsoft certified trainer, Microsoft solution expert, holding a massive persona in cloud world, is here to give you insights about getting started to machine learning. He possesses an incredible experience of almost 22 years that doesn't matches with my age even. His experience is so good, like you can't imagine. So he is incredible in every aspect. So you can guess how amazing this session is going to be. Over to you, sir.
This is amazing. Like my experience is more than your age. Anyways, thank you for being so generous. So let's start with the session. Amazing introduction. So today, what we will do is that we will do machine learning for beginners. Okay. So this is going to be a very introductory course session. And if I do not finish whatever we are speaking about in this session, since this is a community session, we have the liberty of going further and having more sessions like this. So we'll go slow, we'll treat it as a discussion, and this is a community session, so please feel free to ask your questions. I will pause. So the agenda today is that we'll discuss regression. We'll do simple and multiple linear regression. We'll do multiple linear regression and feature interaction. Then we'll do decision trees in Python, cross validation, and then we are doing penalized regression models. Uh, since this quite a lot, if we do not cover, we'll go into the next session. Okay. I have some links to share with you. So what I'll do is that I will also put this in the comment section, and let me just copy this over. This I will put in private chat. This one, and the other one is this GitHub. Okay. So these two, why am I showing you? Is that this channel, so this channel is my channel in which I post a lot of videos. Machine learning playlist is there. There are other ones. Do check it out. There is Intro to Deep Learning, Azure Data Scientist, Spark, Docker Kubernetes and microservices from scratch, statistics, cricket analytics, principal component analytics, pandas. You can see I've had a lot of fun making these videos. Do have a look at it. If you like it, do subscribe. And then there is this GitHub where whatever I do, however bad the code is, I put it in this GitHub, my GitHub. You can have a look at it. The all the code is for this session is here. Ambriji machine learning. Okay, so this is all about the logistics. Okay, so let's jump in and see what are we talking about. So what is regression? I thought that this is a very difficult thing, but actually it's a very simple thing. It's like predicting something which is continuous, right? What is the temperature going to be tomorrow? Based on the previous data, we are going to predict tomorrow's weather. Whether it is correct or not, that is different, but you can do that. Classification is that it's a qualitative variable. Will it be cold or hot tomorrow? So this is a difference when people say of these terms, what is regression, what is classification. So that's the thing. Another thing that people say is that there is supervised learning, unsupervised learning. So what it is like you have been given some data, right? Here it's I picked it up from somewhere, uh, from Western Digital. So you have some data and there is a label. So this is a dog, this is a dog, this is not a dog, this is not a dog. And then you are having a model and you are doing something and you are creating a model. And then when a new data comes in, like this bird is coming in, the model says, so it is a dog. But in unsupervised learning, what is happening is that there is no label. You see that there was a label here, there is no label. So what it groups? similar things together. So the dark is one cluster, another, this one is a one cluster, this one is one cluster. So these are the basic things that is there. So these terms would come a lot, and so that's why I thought that maybe it's a good idea to express these things. Now let's move on to the next part. The next part is, so we will explain what is regression. So regression, actually, you know regression. I'll tell you how. So, what we'll discuss: simple linear regression, multiple linear regression, R square, mean square error, and root mean square, ridge regression, and lasso regression. So, be with me for around 10 minutes and we'll go through it step by step. And then, what we'll do is that once we have all these theory, we'll go into code and see. But now, first, let's understand. And I tell you, you know this. Why? You have seen this equation: y is equal to mx plus c. If you have passed class 9 or 10, you have seen this equation. So that's the equation of a line. The simple linear regression is that. So it has a fancy Greek term, beta 0 plus beta 1x plus an error term. So y is a dependent variable, it is called, and the variable we wish to predict. So we'll see examples of that. X is a independent variable, also called the predictor variable. Beta 0 is the intercept, beta 1 is the coefficient. And E is the error term, where, meaning this one, y is equal to mx plus c, this one is being predicted, but there would be some errors, so this is the error term. So there are more to it, but I'm keeping this lecture very simple. So if you have this line, you see that this is the actual values. These are the actual values, but my line is this one. So what is happening is that there is an error, right? There is an error in between. So this is the error that is happening. This is the error that is happening. This is the error that is happening. So these are the errors which is happening out here. So let's go into a good example of this linear regression. So Professor Ole Aschenfelter, a Princeton economist, had devised a mathematical formula for predicting the quality of red wine vintages in France. So what it is that, so the wine, so the price of wine depends on a lot of factors, and we will see it with the case study later. And this professor, an economist professor who is not a wine tasters. So you have wine tasters, just like you have tea tasters, they have got wine testers, and they tell you the price of the wine. But this gentleman was not a wine tester, he was an economist, and he knew only these many other things he knew, but he knew linear regression. So he used linear regression and predicted the price of the wines very correctly. So the people who were spending a lot of time in wine, they said it is ludicrous and absurd, but fortunately he did it very correctly and used this linear regression to do it. We'll see it in practice in the next lecture. So here is another, which is multiple linear regression. So the sales is being predicted by the spend on radio and television advertising and the spend in store displays. So these two variables are predicting the sales. Okay. So wine price. So this one I was talking about. So these are the factors that is influencing the wine price. The temperature during the harvest season, summer temperature, winter rainfall, harvest rainfall, and age of the wine. So these are the various factors which are affecting the wine price. Okay. So this is another example. So what we are trying to do is that we are trying to find out the price of the house. So the price of the house is quite difficult to get. So these are 13 factors that are there in getting the house price. So you see, let's meaning don't think of it as mathematics or anything. Think of it as a very practical thing. So the house price is dependent on the crime rate, the proportion of the residential land. So basically, it says whether it's a business area or not, the non retail business, whether it's close to a river or not, how good is the environment, the nitric oxides concentration, average number of rooms per dwelling, proportion of owner occupied units built prior to 1940. That means how old is the neighborhood. Then there is a weighted distance to five Boston employment centers. So that is the distance from an employment center. How close is it to the radial highways? The property tax, the pupil teacher ratio, the black proportion, and the lower status of the population. So these are the various factors you see, various combination of factors which is affecting the house price. So this also you can solve by linear regression. So this is one example. Now, now you can say that once I build a model, then how good is it? So we'll skip this for the time being because it's quite involved. We'll go through code and then we'll see that this thing, or we can just go ahead and explain it and then we'll see the code. So so we introduced two terms, the total sum of squares and the sum of square errors. So what is the total sum of squares? It is a very simple thing. So this is the mm, actual value. That means we are trying to predict, say, suppose the wine price. So actual value minus the average of the actual value, that is average of the wine price. And then for each of these data that we are having, we'll square it. If you don't understand it right now, all these English blah blah things, we'll see it in code and I'll show you in practice of how it is done. And then there is the SSC, which is the sum of square of actual value minus the predicted value. And R square is 1 minus SSC by SST. Now, you can understand that if the R square is 1, that means that this is 0. Okay. So, what it means is that the this this is a good model, but if it is 0, that means that it is very bad. Why? Because I didn't do anything, I just use the average of the dependent variable. So that's not a good thing. So R square meaning 0 is no improvement from the baseline. So the baseline is the average of the wine price. Don't worry if you're not getting it, we'll see it in code and we'll go through once again. So this is the same thing, but here we are introducing another term called the root mean square, which is the square root of the mean square error, and the mean square error is the SSC by the number of observations. This is another metric. Very simple. This is a much more simpler metric. It is the sum of square of actual value minus the predicted value, and then we are dividing it by the number of observations, that is making an average, and then we are taking the square root. Again, don't worry, we'll see it with an example. Now, there is a concept of a penalized regression model. Now here, uh, the penalized regression model is slightly different from the root means, from the other uh, root mean square error. In this, what is happening is that it has got a number of parameters. So there is, we are trying to minimize the following for the ridge regression. What we are minimizing, this is the sum of squares. This is the predicted value minus the actual value, and this is we are squaring it. And then for the ridge regression, what we are minimizing is that the coefficient which is there, we are squaring it, and then we are summing it up and multiplied by tuning parameter lambda. So that is the regression, and the lasso regression is the same. Only thing is that we are taking a mod of the coefficient. So this is a theory. We will see this in code step by step so that you understand in a much more better way. For now, what I'll do is that I'll take a pause so that I take questions and maneuver my presentation for the next part, that is when I'm going to the code. So let's take a break and I'll see whether we have any questions. Okay, okay, no questions. Okay, okay. So let's jump in and go to the code. Mm. So the code is there in GitHub. So this is the Wine linear regression. So what we are doing is that we are first importing the libraries, and then we are reading the wine data set, the wine.csv, which is the training set, and it has got a couple of variables: year, price, winter in, average. AGST is what? Average growing season temperature, age, and France population. Similarly, we are having this in the test data set, but in the test data set, it's also the same thing. So the simple linear regression is a very simple thing in which we are using only one variable. What we are using is that we are using the features which is one variable and which is AGST. Okay. And now we are doing a model of linear regression. We are fitting the model, and here we are putting in the one which we are predicting, and we are getting the model, and we are getting the coefficient and the intercept, and then we are doing a predict to get the predictions. Right. Now we can do a predict. We can do a predict, and now what we want to do is that we want to find the root mean square error. So how we can find the root mean square error? The root mean square error we have learned, right? Predicted minus the actual value. So this is the predicted predicted value, predictions minus the actual value, and then we are squaring it up, and then we are summing it up. So whatever we have shown in our mathematics, we are doing it in code. So this is the sum of square errors. Okay. And then this is the mean square error, which is the sum of square errors divided by the number of observations. This is the mean square error. And then what we are doing is that we are doing the metric, which is the RMSE, which is the root mean square error. Now, we did a lot of things, right? We could have done the same thing just by using the matrix dot mean squared error, and you get the same result. Similarly, for the predictions test, we are doing a model dot credit predict on the features, and we are getting the test predictions. So root mean square is also given here. Now, the next thing, what we will see is that the concept of correlation, but we'll come to it a little bit later. But let's go on to something that we discussed, that what is the difference between the multiple linear regression and single linear regression. So the difference is that in the single linear regression, we used one variable, but in the multiple linear regression, we are going to use multiple variables. So here what we are doing is that we are using agst and harvest train, and then we are fitting the model, we are getting this model, and then we are getting the model dot coefficient, which is the one that we have seen, right? So here it is a simple linear regression. In the multiple linear regression, what will be the beta 0 plus beta 1 x1 plus beta 2 x2. So here there are two variables, so there will be two coefficients and there is one intercept. Similarly, we can predict by model dot predict, and then we get the mean squared error. You see that it is 0.42, the mean square, the root mean square error, and previously it was 0.47. So this has uh, no wine data test. Oh, so this was better. The single linear regression was better. Now, what we do is that the next regression model is that we are increasing the number of features. Previously, there were two features. Now we have got three features. So what the equation now is, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus the error term. So here what is happening, same technique, and you are seeing that there are three things that is coming into picture. Sorry, there are three variables. So beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus error. So there are three terms and therefore there are three coefficients which are coming in. And then there is the intercept. We do a model dot predict again, and then we are getting the mean squared error again. You see the mean squared error has decreased by increasing the number of parameters. So the lower is the error, the better is our model. Now we are also using another one, winter rain. Now you see in the winter rain, what is happening is that there are four variables. So I'll have four coefficients which are coming in, and we are having this intercept. So what is happening is that after I do a fit, then I can do a predict, and then I can see that this is a mean square error. Now, continuing the same way, I now introduce another variable known as the France population, and now there will be 1, 2, 3, 4, 5, 5 variables, five coefficients, and one intercept. But now you see that increasing the number of variables from 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 4 to 5 did not reduce the mean square error. Now, why this is so? It is because of this thing, that these two quantities, the winter rain and the France population, are correlated. Correlated meaning, you see that this one, if I do a plot of age versus France population, that means as age is increasing, the France population is decreasing. So, if there is a relationship between these two variables, then and it is in the model, then it is called multicollinearity, and multicollinearity should be avoided. So this is why these two variables are interrelated, therefore they are not adding any value to the model, therefore we should not use France population in the in our model. So this one was better, so we should stick with this. Obviously this is not a great one, because meaning we have to validate in different cases. We'll see it later of how we can really create a robust model. But what I want to give you the concept through this session is that how you can increase the number of features and see of how the error is being increased or decreased, and this is how we can see of how we can do model building. I will take a pause here and then we will move on to the next session. Let me see if I have any questions. I do not see any questions. If you have any questions, feel free to ask. Or if you do not understand anything, please let me know. Okay. I'm just wondering, uh, how many people are there viewing so that I have a view?
So like now, right now, the 37.
Okay, so that is very good. So if there are 37 people, if you have any questions in between, please do ask, because this is a good time before I move on to the next part, which is about the feature interactions.
So actually, there is a question now.
Okay, okay. So how do we decide which use, like when to use lasso and reach? That's a great question. I will come to that. There is a technique called cross validation that I will discuss, and I will tell you exactly of how to do it. This is a great question. This is that I will address later. Okay. So let's move on to another example, which is a linear regression with Boston data set. So here in the Boston data set, so this part is also available in this channel, uh, in this playlist. So regression, so this also there is a lecture on this. You can see this lecture separately, the part which I have discussed. Now I am moving on to this part, which is multiple linear regression and featured interaction. So here what I am going to do is that I am going to use the Boston dataset. All the code is in GitHub, so you can see that code over there. So this is the import of the libraries, and then you read the data set, and uh, then you can and then you can um, read the data set. And one second. So you read the Boston data set, and then um, you can so this once you read the Boston data set, you will find these variables here. So this is what we discussed here. So this data, and we are going to predict this variable, the median value of owner occupied homes. So now what we want to see is that the relationship between lower status and median value of the owner occupied homes. So this is a plot in which it is there, uh, in which as the lower status increases, the median value decreases. So this is a plot which you can plot it. Maybe we'll have a separate session of how to do plotting. You can see this code of how we can plot, but these plots are very nice. So then what we do is that we divide the data set into two parts. Now, first we are doing linear regression. So we are using this LSTAT, and the variable which we are predicting is MEDV, the median value. And then we are doing a test split. What the train test split will do is that it will divide the data set into two parts. I think the initial value is 80/20. So that means 80% will be in training and 20% will be for predictions. So we are using the simple way, the linear regression. So it is, we are doing linear regression here, and then we are doing a train test split, we are doing a fit, when then we are doing a prediction, and then we are doing the square root of it. Now here also we are getting the coefficient and the intercept. Okay. Now if we do with the age of the houses and the median value, it also says, like, which is very correct, right? Like as the age increases, the median value also decreases. Now this is multiple linear regression. Why it is multiple linear regression? It is multiple linear regression because we are introducing two features now, LSAT and age. So that's why we are following the same strategy of train test split, model fit, and then the predictions, and then we are getting the mean square error, which is 6.56. Now we can find that with this a better, the 6.56 with the and 6.665. So this one, age of the houses, once I add it, it is decreasing the mean square error. So this is a better model than the single linear regression. Now we can do one thing instead, we can include all the features that is there and do a multiple linear regression. So it includes now all the features. So this is all the features and we are doing a multiple linear regression and we are getting 5.45, which is very good, which is much more better than that. Now, um, we are now taking another one in which we are dropping the tax and the we are dropping tax from the multiple linear regression. So that means we have included all the features, but we have excluded tax and we are doing another one, which is 5.52. We are getting as a root mean square error. The same technique. Again, we are doing with Indus and we are getting 5.45. Now, what I want to show you is something quite interesting known as, so these are like the intention of showing you this. Another example is that you can do single linear regression, you can do multiple linear regression, and in this way you can try out different combinations of it. But there is a way in which you can create new features. One way of how you can create new features is that by combining two features, like this one, which I have done, which is called a feature interaction, in which I have multiplied LSAT with age, and this is a new feature. This is called a synthetic feature. This we have created, and this we will include it in our model. So this we have included it in our model, and now we are fitting it, and we are getting one mean square error 5.44. Now you can see that this better 5.44, and this one was with all the features it was 5.45. So this is with all the oh no, uh, it is slightly better, but it is not better than this one. So we can see, you can see in detail that which model is better through this. But this is not a very foolproof method. The foolproof method I will tell you later. But the intention of telling you this is that you can have features. All these features are there in the data. But can you produce new features? Yes, you can. How can you produce new features? There are various techniques of creating new features. One technique is called the feature interaction, in which you can multiply these two features. That means combine the effect of both these two features and see of how what effect it has on the price. So this is one technique that I have illustrated here. So similarly, this discussion is also in this YouTube channel, and this is a video which explains this. In the same way, what I would do is that I will take a pause and see if there are any questions. Okay. Okay. Yes, Neha, that's a great question. The generalized linear models. This session is not about that. Maybe that's a great suggestion. I will have one lecture on generalized linear models later on. But that's a great suggestion on that. Mm. So, so this is about this part, and then what we will do is that we will jump into the next part, that is trees. Okay, so the trees. So so whatever that I would be saying, I have taken a lot of inspiration from this book. It is a free book. Please feel free to um, get into this book, an introduction to statistical learning with applications in R. The code is in R, but that doesn't matter because the theory is generic, so you can use it. The well-known ISLR, this is a very good book. So trees, what it does, it segments a predictor space into a number of simple regions, and the set of splitting rules used to segment the predictor space can be summarized in a tree. Hence, this approach is known as the decision tree method. So, what it happens is that predictor space that we found, right, the x1, x2, x3, that is structured in the form of a tree. And what the usefulness is that it is very easy to interpret because everybody understands what's a tree. It's like a decision tree. There is nothing great about it. We have seen these decision trees everywhere. It is simple and useful for interpretation. It has a low prediction accuracy, and combining a large number of trees can often result in dramatic improvements in prediction accuracy. This is a great thing. That means if you have a single tree, it's fine, it's easy to interpret, but the accuracy is low. But when you combine a lot of trees together, which is a basis of of various algorithms such as the random forest and the boosting algorithms, which we will see in the later lectures, not at this point. So these come with greater accuracy, and but at the expense of interpretation. So here I will choose the data set which is the house sales in King County, which is a very simple data set and which has got 21,613 rows. And these are the various columns that are there in the data set. You can see it has got date, price. Price is what we are going to predict. The others are the bedrooms, bathrooms, square foot living, square foot lot, floors, waterfront, view, condition, grade, and all these other things are there. Now, how it breaks up is very interesting. So there are a lot of variables, right? So this is a high level tree and it breaks up into two regions. And these two regions, what is happening is that once it breaks up, it tries to minimize a mean square error. If you have forgotten or what I had said, that mean square error we studied previously. So it is using in such a way that the mean square error is very less in these two regions. So this is region 1. So this is region 1, this is region 2. And this is a mean square error for this region, and this is a mean square error for this region. But what is the value of of the house which has grade less than 8.5? It is 437,284. How did I find it? I found it by making the mean of all those data which is less than 8.5. So this any data that is less than 8.5 will come into this region, and the value, the price will be 437,284. You see how I have done? Very simple. Less than 8.5, I've calculated the mean, and this is the one that I'm getting. Similarly, for the right one, you see it is greater than 8.5, and it is 95 9962.411. See, it is coming the same. So the strategy is very simple. It is splitting in such a way such that it divides into regions, and the region, the value of the data in that region will be the average of those data that is falling in that region. Now, this is from the ISLR book. So what we discussed till now, it is written in a very mathematical way. It is saying that you divide it into j distinct non-overlapping regions. So here it was R1 and R2, and then for every observation that falls into Rj, we make the same prediction, which is simply the mean of the response values for the training observations in Rj. So that was, we had said, it is a mean of this region. Of all the samples which are less than 8.5, we are getting it. So follow this book. It's a great book, but sometimes what can happen is that um, we may not be very comfortable in reading books, so that's why this session is going to help. So this is a more graphically represented region 1, region 2, and then you can have subsequent more regions. And it is a top down approach, and it's a greedy approach. It means at one level it tries to minimize what it sees at that level. Now, this is a two level tree. What is happening here is that similarly, what is happening? It is grade is less than 8.5. Then we have two things. The latitude is less than 47.534. And then you have got two regions out here. There are two values which are coming in. Similarly, for square foot living, also we are having two regions, and the same concept is there. So that means the data which is grade less than 8.5, square foot living less than 4185, has this mean square error and also has this value. So this is what it is. Similarly, we are going deeper, right? We are getting with three levels. The concept still is the same. Once you get a hang of this concept, so this also is doing the same thing. So less than 8.5, less than 47.534, less than 2035, and then also you are having this value. So this is how it is growing in. So, so that is all about the theory of trees, and then we will go into the implementation of the trees. But before that, I will take a pause and see if there are any questions. Yes, that's a great question. Um, how to decide the splitting point is greater than 8.5? Um, what I would suggest is that you try to find out this thing. Think of, I'll give you some hints. Uh, I'll give you some hints. See, this grade has some unique values. Okay. So, can I take all of these unique values and see that which one will give the lowest MSC? You try to find out that whether it is that way, or it is doing a simple moving average. I think scikit-learn is doing a simple moving average um, of these unique values and getting the 8.5. What I would suggest is that these are the hints that I'm giving you. Make sure, yes, that would take a lot of time, but um, fortunately, the computers are very fast, and that's why it is easy for them to do. So you try and see this with this data set, that whether that's the one that how it is doing. But I think that's how it is trying to do. for all the values it is checking, that unique values, or what it is doing, it is taking a simple moving average and getting those values for those values and trying to check the mean square error. Try it, and I think let's engage on this discussion here. There is this this is a place where I have done the whole with these decision trees in Python. We can engage in this discussion, but I tried doing it, and you also try and see, and let's discuss on that. I think what we'll do is that we still have some time left. So I will show you the decision trees with Python. I don't know whether I did that experiment over there or not. No, I have not done that. But please do that and see whether it is making sense or not. First, try with all the unique values, all the mean square errors, and whether that's the way that it is choosing. And then choose that you have say 10 values, you can choose the simple moving average of two values together, meaning choose two values and then take a simple moving average, then choose the next two values and take a simple moving average and see of how it is done. Now let's see, but that I think would be a very good discussion for the whole community. And I tend to continue this series with more things. Like I think not have time for cross validation. Maybe next session we'll do cross validation, penalized trees, and all those things. But we have some time left. We can do the decision trees. Let me run through it. The technique is the same. The decision tree regressor is the one that is being used, and we are doing a plot, and we are doing the same technique. We are doing a decision tree regressor, we are doing a fit, and this is to get the model in a picture, but the concept is the same: fit and then predict. So here what we are doing is that we are doing this tree, and you can see of how this tree is done, and then we are doing the predictions with the predict. So the concept is the same: we fit and predict with scikit-learn. And then you can see what the analysis that I had done on the mean square error, all those things that were in the PPT, all those things are done in code, and you can see the samples on the left analysis, and on the right analysis you can see all these things. For depth 2 also, I've just made the depth equal to 2, the create tree. If you see the create tree over here, there is a parameter here, the depth. So I'm just changing the depth here and I'm making it. And also you can see all these other things. For depth 3 also you can do. There is also a concept of leaf nodes. So instead of using the depth, you can have the leaf nodes, which is 3. That means what I am doing here is that there is a parameter, the max leaf nodes, and that's how you are doing this. So that's how we are doing all these things. So this is a code for that. But for that question, I would suggest that you try it out and see if that's the case of how it is. We know that the splitting is happening at 8.5. If your question is why 8.5, should do that and see that, find out the unique values. All the code and the data is in GitHub, so you can try it out, and let's have a discussion also in this community to see that whether it is making sense or not. If not, then I'll also try to see whether that's the way it is doing or not. So what I'll do is that still we have 10 minutes more. Maybe I can introduce the concept of cross validation. I just see if there are any questions. Okay, no questions till this point. So before we take leave, this is a very interesting concept that I'm going to explain, that is cross validation. Please bear in mind this is one of the most interesting techniques there, and there are various ways in which we can do cross validation. So cross validation, this is one of the techniques of cross validation. What it does is that the training set is divided into k pieces, and then we use k minus 1 pieces to train the model and to test the model on the remaining piece. And we repeat k times, and this helps in choosing parameter values for better accuracy. So, what is happening right now is that, say suppose for the pass one, it is training on fold 1, fold 2, fold 3, and fold 4, and then we are testing on fold 5. For the other one, we are using fold 1, fold 2, fold 3, and fold 5, and then we are testing on fold 4. Here also the same thing, you see the technique now, fold 1, fold 2, fold 4, and fold 5, and they are testing on fold 3, and similarly fold 2 and then fold 1. So here what is happening, there was one question whether I should use technique 1 or technique 2 or technique 3. The thing is, the trick is you can apply various cross validation techniques to see whether your model is performing across these folds or not correctly, and the one which gives a good cross validation score, that model is better than the other model which gives a bad cross validation score. Another thing that is there is called a bootstrap sample. So what is a bootstrap sample? This is another very interesting concept, and I'll keep on revisiting this. It is a random sample of the data with a replacement. That means I have got the whole data. I'll take a sample of the data, and but the bootstrap sample is that after a data point is selected for a subset, it is still available for selection. So the bootstrap sample will have duplicates, and some samples will be selected in the bootstrap sample while the others will not. The samples which are not selected are called out of bag samples, and so these are the things that is being there in this respect. So the model is created on the selected samples and predicted on the out of bag samples. So this is about the cross validation and the bootstrap. In the next community session, what I will do is I will revisit this because this is a very important concept. I will take a pause here because there is no rush. We still have more sessions. We can do the penalized regression models later on. And that's what is. I will end it here and wait for questions so that we can continue with penalized regression models in the next session. So, if there are any more questions, we can have a look.
So I guess if anyone is having any question, you can feel free to drop your question in the comment box. Okay. Okay, I guess there is no questions. So it's very insightful sessions for us. It's our pleasure to listening you. Hoping to get some more likewise sessions from you. Thank you, sir, for being here. And as you said, like we will be discussing some more topics, and we will be continuing this series. And thanks for joining. And I hope everyone you got the concepts that sir wanted to share. We the last announcement is like we have a wonderful community of around 10K plus students to engage in Discord. So here is the Discord link that I'm sharing in the comment box, so you can join us. We do a lot of amazing things there. And okay, so one last thing is uh, this is the connection LinkedIn of Amrish sir, so that you can just connect him through LinkedIn, so that you can get some idea about what he's doing, what he's been incredible with his entire journey. So you can just connect with him. So this is the link.
and
So thank you
and
guys.
also and also you can put the YouTube channel where I am quite active. So put
Yes,
the YouTube channel also there. So if you like whatever I am speaking, you can subscribe there and be active,
yes.
ask questions. I am also learning, so that doesn't mean that I know everything. The more I, the way that you ask a question, that why 8.5, it came while I was teaching myself, that why 8.5. So the more you ask questions, the more as a community we will learn. It's not that I know everything. We are going to talk about what is this channel. Where?
Okay,
Oh, okay,
so
okay. It came. Okay. So this is
okay,
and the GitHub is also there. The GitHub also you can post. The GitHub is also there. So the code,
yes, sir.
all the code that you can see is also there. Obviously, I don't write great code, but you can have a look. You can, we can all improve. So that's it. And thank you for listening to me. Thank you for your time. Hope the time was well spent for you. That is the most important thing.
So thank you, sir. Thank you, everyone.
Thank you. Thank you.